Hello, everyone. My name is Andrey. I'm working as a software engineer at Meta, and I'm doing experimentation. It has happened that every several years I change my domain area, and I have to learn a new one almost from scratch. The same has happened with A/B experimentation or testing not so long ago. It appeared that experimentation is not so easy and to understand, and I want to fix it with these presentations. Today is our second part of A/B experimentation in layman terms. The first one was about a month ago, and I hope that you are familiar with it, or at least briefly. If not, no worries, I will do a recap and we will try to reference it whenever possible. We have more terms which should be used today. As before, I consider this presentation mainly for the software engineers. This is not because I like them more, but I believe just my examples and level of knowledge is most closely relative to this group. And if you have a good statistics background, it should be maybe too easy for you for in this less level of description. But anyway, welcome everyone. On the format. That will be no Q&A at the end. Sorry, this is company policy. I can't do this. But during the presentation, if you have any questions, please drop them in the chat. And if they are in context, I will try to answer them. And yeah, at the end, also, I will provide an email. Feel free to message me. I will also try to answer your questions. Session will be recorded and it will be available in several days or by the same link as you have just joined. Okay, let's get started. Last time, we were passing through the story of one experiment, and today we will be focusing mostly on statistical approaches. Of course, so we will go through sizing with two types of errors, what is statistical power, and after that we will switch to the empirical data, which will include A-tests and bootstrapping technique. Built-in story of this same the same style that it was before with a single experiment, it become harder and harder. So I will focus today more on the statistics, but I continue to visualize and try to make it as obvious as possible for each term that we will be using. Так, our first part, recap from the part one. So in the previous presentation, we started from this simple idea of to test what's will be the difference between green and red button if we change it on our website. Just a simple change. We went into more details on this. We just started measuring clicks and views on this side. After that, we introduced our first metric, which is click-through rate, just a probability whether not anybody click on this button or not. After that, we introduced what is binomial and normal distributions, then introduced standard distribution and or Z distribution to be able to just normalize our results. And finally defined what is confidence level and what is confidence interval and margin of error. With this, we will be able to finally see the results and approve that our site has better results with red button. But that wasn't just the end. We worked further and introduced what is null hypothesis and alternative hypothesis, and moved to the differential scale, which gave us opportunity to measure results differentially. So we just see the difference from 0 into some direction. Also, it was required to introduce combined or pooled standard error, so we can combine different results in one single number. And finally, so the same result, we see the difference, but it is measured towards 0 point, not at some degree with two bars. Why I'm talking about this one? I'm talking and try to cover a bit because we will be using these terms and this knowledge today extensively for the next techniques. And our first topic for today is sizing, which means how to compute the right number of views for our experiment. So we make sure that this result is significant, we can trust it, and what factors affect this number of views which required to see the difference. So let's start from the problem statement. For instance, we see this picture. We just made a test and we see this picture after some test of green and red button. Does it mean that this new version is better than previous one? How likely we deliver some improvement? Or is it a natural result or negative? The difference here is small enough and the graphs are not clear. We definitely see that confidence interval of the red graph is crossing the 0, so we can't say for sure whether it's bad or not. So it means it is most likely a neutral result, and we require one more test to prove or disapprove this idea. And it means that this current test is lost because we were hoping to see the difference. Also, we can say that this test doesn't have enough power. I will talk about power in a moment. Now, let's look how numbers of samples that we collected for this experiment into the width of this confidence interval. Because if, for instance, if we can make it smaller a bit, the test should pass. And here are our formulas from the last one, the last presentation. Let's reverse engineer it a bit. What's the confidence interval? So this the formulas. For now, we know that confidence interval is just 2 bits of margin of error. And margin of error is just multiplication of z-score, which is a constant level, usually, about, so we can fix it on 95%. And multiplication on the standard error or standard deviation. It can be used interchangeably. So, and this standard error in turn is the square root from probability multiplied by inverse probability and divided by number of samples. This exactly number of samples that we are looking for. If it means that if we increase number of samples, this whole number of this confidence interval becomes smaller. Of course, it becomes smaller not linearly, but in the square root of it. So, for instance, on a previous slide, we saw a change of the change was about around 0.18, while the measurement margin of error was 0.2. If we increase number of samples, we can measure margin of error can become 0.15, which give us a positive outcome for the experiment. Of course, I bring these numbers. I didn't compute these numbers precisely, so It's just for the example purposes. Don't try to recompute it. But the idea, again, like this. So we are improving number of samples. We are narrowing down the confidence interval. Yeah, so the question is, does margin of error come from the business acceptance level, from business practical point of view? So yeah, I'm not touching practical aspect here right now, but yes, so that depends what the business needs. So in some cases, business can hunt for any improvement. For some cases, you want to introduce practical significance. And for instance, say that everything that below some threshold is not interesting for us. So for now, I not touching this practical. So it can come. You just want to make sure that you see the difference, and you can set a threshold when it's needed. Yes, that's how it works. And there's a special mention about the ideal world. So ideally, we want to see this connection between square root of 1 divided by n. But in real world, it's a bit more complicated, but we don't touch it today as well. It's mostly because when the experiment become longer, first of all, if you want to collect more samples, it affects by other factors, and the confidence interval might not become smaller. It might still become the same, and yeah, that's another problem. To be a more advanced topic. So let's look at an improved version. With this version, yeah, we edit some number of samples. We make our confidence interval a bit smaller, and we see the improvement. Yeah, it's tight. This experiment show that we have statistical significant result. But are we good enough? And I think this depends. The problem here is here in the gray zone. If you look carefully, it starts from the right cutoff of the original version and goes all the way to the left of the improved version of the red graph. The area of this gray zone is responsible for the chance of not getting any improvement. To put it simple, proposed change doesn't actually change anything. So you do not see any profits. Yes, yeah, exactly. It might be also connected into business practical needs. Let's collect all the improvements on the one page, so I can describe them in more details. So here you see it all in one picture. First of all, I want to remind what is null hypothesis and why we work with it. Null states that there is no difference between green and red button from or red graphs, and we are making a decision to reject it or not. And when we see the purple area on the graph, this is the first type of error, and you are already familiar with it. It is opposite to confidence level, which is fixed usually on 85%. This is also known as false positive results. So it is when we decided that there is change, while in reality there's no change. And yeah, but we decided there's a change, and we delivered the new version. And the second part is the type is new. Second type, it appears when we decided that there is no difference, while it actually is. We're literally missing opportunities here. This is also known as false negative. But more practical outcome of this is the opposite part of it, 1 minus beta. So beta is a second type of error type, and first is alpha. So 1 minus beta is called a statistical power. And this is what we are looking for. The more power we have, the more confidence that we do not miss the improvement. Same as for confidence level, it has some typical numbers which are fixed at some level. And usually in industry, it's about 80%. But it is not strictly like this. It balances between not delivering a change versus delivering an empty change, because delivering nothing can also cost us something. Like we still to do some movements, to release some new feature, to release some new version, and so on. So this is a practical needs. In general, type 1 error has more negative impact than type 2 errors. That's why they have the default value on 95, and type 2 errors usually 80%. But it is frequently, this case still can differ. And let's look on our page if we move forward on our example, if we move forward and increase even more number of samples. In that case, our graph becomes even smaller, width of our graphs. And this is the picture that we actually want to see when we deliver something. So in this, how we want to it be distributed. Taking significant level on 5%, power on 80%. But yeah, that's the picture. But what do I mean? I still didn't talk about the numbers and how to get number of views. It is all a theory. Yes, I didn't this. And it's just because the best way to do it is just to use online calculator or some embedded to it, because the formulas, the reason you want to compute area under the curve. It requires integration, and it's maybe not the nicest way you want to invest your time. So also it depends in the formulas, it depends on this which spectrum of probability you are closer. So in the middle or in the borders. Here's an example. I typically use Evan Miller org site for online calculations. This is not an ad, just the reality, a small screenshot of it. And I put some numbers for the correlation of it. So we just covered the data that needs to be put into this calculator, so it will be easier to understand the problem. And this calculator still follows the familiar formula on the slide. And as you can see, a number of samples is symmetrical on both ends of probability. I mean, if you look at 20% probability or 80% probability, we get the same number of samples. But if we look at something in the middle, like 50%, the numbers are pretty high. Yes, that's how this formula works. Also, this is the big difference between what's the number of confidence, what's the size of confidence interval you want to allow. In this case, it's called MDE, minimum detectable effect. So the smaller effect you want to measure, the more samples you need. And this is a huge difference. For instance, if you want to measure 0.1 MDE, and it requires 3,000 times more samples than, for instance, for 2% MDE. and 8,000 times for 5% of D. And of course, it is impossible to get an MD of 0. It's ideal world, but yeah, this is math. This is limits. You can't do this. So yeah, this is the first part. And let's move to the second one. Using empirical data. All the computations we had before were analytical, and which means it doesn't take real data in distribution into account. It means in many cases you want to compute confidence interval or do analysis of expectation system based on the real data set. And in some cases, it can be also like end-to-end testing of the system, metrics distribution, or something else that we want to test inside the system itself. Usually, when you believe in a system and you have just basic metrics like CTR, you don't need this, and it is okay to use analytical assumptions. And especially when you're just getting into A/B testing, it's maybe just overwhelming for you. But don't rush to do this. But if you don't trust any of this part of the system, or you have more complex metrics, use it, and you will get some advanced results. So the main target is that you are suspecting that that's something not normal with your metrics. The whole process of getting into this empirical data is very close to what was defined in the previous presentation as a binomial distribution with the coin flips. I will start from it so it can be easier to understand. This is a picture just from the last previous presentation. So what we want to achieve here, we want to build a probability histogram out of coin flips. So yeah, we just throw a coin and count the numbers, do it 100 times and repeating 10 times, building some histogram and distribution of probabilities, doing 100 times, doing some distribution of probabilities, go. But we actually doing A/B testing. So flipping one coin is not very interesting. In this case, we want to compare something. And let's evolve this idea and to switch to differential scale. So we can see what's the 0 and what the differences between our A and B versions. But of course, what we will compare in this case. And we can compare the same coin or a very similar coin. And this type of comparison will be called a test. So we compare same coin or same state just to repeat the test. This is a special type of A/B testing when you compare versions from without changes. And now we can do comparison between these two A and A versions and build the same histogram, but it will be not around 0.5 probability as it was before, but at 0. Okay, the way it's working, yeah, if you look on the distribution on the right corner, so you want to expect the graph on the left, and but the reality is you see something like on the right. So some circumstances can change, and you just see some differences. Why do we want to do this? So let's assume we ran an AI experiment and got a statistically significant result. What does it mean? Why did we didn't apply any changes? It is an issue with the system, and that's one of example. Actually, the three reasons to have AI tests. First of them is to do a sanity check. Second is to estimate variance and calculate confidence intervals out of this. And the third one is to directly estimate confidence intervals without doing any assumptions. So I now have to switch to a more concrete example with the spreadsheet, and we will deal with them one by one, so it becomes more understandable. This is sample dataset. We want to validate our system with AI tests. It means we want to have a statistics over statistics. That's why we need many AI tests. In this test, we have 20 results for small tests. They called 1% tests, and 10 tests for larger size. They called it 10% tests. Of course, as we can't have more than 100% traffic, we assume that we can't do more than 10 tests. So that's a limitation of the system. In further slides, I won't be showing the full length, full size of this dataset, but it is still present. It's just excerpt from Excel, and it is still in place. I just cut it till the black line in the middle. And about the third column, I will explain it just on the next slide. No worries. About this highlight as well. So let's start from the sanity checks. We want to see that our tests, ideally, forming a normal distribution. With more and more tests, it becomes more normal. And it is still must follow the same pattern as with the coin flips above. If you look at the top right histogram, this is exactly what we want to see. Bottom one, it's kind of normal, but we have fewer number of tests, so it's harder to justify. That's one of the reasons we want to have more tests. Second part of this sanity check is that the variability getting lower with a high number of samples. Ideally, we just mentioned about the sizing. We want to see the correlation as 1 divided by square root of n. Lowering of variability. In reality, it might not happen, so it might still stay high. For current examples, if you look more carefully on the difference between numbers in a larger experiments, it is really 1 degree lower, so it's getting close and close. On a small experiments, you can see, orange marker is also a good point here. If you see these results, what does it mean? It means that we detected one statistically significant result, and this is a bit strange. We didn't do anything. How to react on this? So let's recall that we set our confidence level when we do these computations on the 95%, which means 5% of our X-test still can show something statistically significant. And if in this A test this number stays about 5%, that's fine. That's exactly what it is expected. But if it becomes higher, this is a red flag. You should investigate why it's differ. And with these two cases, it is an exact reason to have different sizes of A tests. So you can definitely see that with smaller one, it is much easier to build a histogram, while you need to compare them with the larger ones to ensure that variability actually lowered. In some corner cases, it might appear that there's no true single probability, and no matter how large a test you run, it's still not centered around some kind of probability. Yeah, this is an example. This is very weird and corner case. It is not expected to be a CTR metric, but it technically can happen. And if you're not sure in your metric, this worth checking. So second case. And this one is about getting confidence interval out of empirical data runs. These things become a bit harder, but still doable. I added just 3 columns, command or combined or pooled probability per each experiment, standard error per experiment applied by just general formula, and margin of error, which is just multiplication by z-score of 95% confidence level. On the top, above the standard error, pooled error, this is the number computed by standard deviation out of differences between the experiments. So in any spreadsheet standard library, usually present a standard deviation function, which is applied by the formula on the left corner, which is just a square root of deviation and divided by number of the tests. So yeah, we can just pass the array of differences to this formula, and it will show us the number. And this number should be comparable to the standard error of. We can out of this number, sorry, we can extract margin of error, and we can compare these numbers with the, each particular experiment. So for provided example, the standard deviation out of these differences is lower than for each particular experiment, which is quite useful in this case, and you can use it. But the main idea of doing this is that this number is much more stable because you are averaging across all the tests. It is much more stable than a margin of error of each particular test. And yeah, you don't need to rely on the just analytical results. So this is the second case. And the third one. Third case requires some theory. We want to inherit confidence interval directly out of provided result. It should look very similar to this picture on the left. So just describing. We put all the data points on the axis, then symmetrically trim left and right tails proportionally according to our confidence level. And for instance, in this picture, we have 40 dots. It means each dot weight about 2.5% of total number of dots. With the typical confidence level of 85%, it means we can remove one outlier dot on the left and one on the right. Bit of what's left will be our confidence interval. In that case, it is finally can be asymmetrical and looks more realistic. But we have some problem with this scenario, no matter how cool it looks. The drawback of this is that you need many AA tests. Right now, it is about 40 tests, and you can remove only one dot on the right and on the left. If you have 20 tests as present in our dataset, a weight of each dot will be about 5%, and you can't see the difference between 90% and 95% of confidence level, which means, yeah, you can measure on the 10% differences between confidence levels. So let's apply it to our dataset, what we have. So we have only 20 tests, as I mentioned, and we can do, at best, 90% confidence level. It should look like this one, and one statistically significant difference, it looks okay, because it's exactly what we just got. Now we have an interval of potential confidence interval, which is still fluctuating, but ideally you want to stabilize it. In this case, if you add more and more A tests, it becomes stable. And with a high level of confidence tests, yeah, you will see pretty stable results. The confidence interval will be always the same, and you just cut the tails. Can we do something more clever than just increase the number of A tests? I believe that every system has a capacity limit, and you can't just increase your A tests for calibrating the system every time. And actually, we can. This is still require lots of data, but it is much more doable and much more clever approach than just reiterating on A tests. And this method called Bootstrap. Let me try to describe it in a very simplistic way. So the result of this test, this method, looks very, very similar to A tests, but yeah, we need to make some trick. First of all, you want to run a large A test. Real, just a large test. And keep the data about each request of you. So about each data point you have, which you get into your system, you want to keep it, and not just summary result. Then, randomly, you pick a subset of the equal, same size, I mean, equal between each other, and treat it as a separate experiment. You can pick as many subsets as you need, just do it randomly every time, and keep the same number of samples that you pick into your data set. And here's the main requirement is the randomness of how you pick the data. Of course, if you want to go at scale and you have too much data to store for and compute every time, you can pre-aggregate it and say that you're not storing each particular request or view, but you keep the data about some kind of segment, which is some aggregation of a group, which is an aggregation of your requests, or in this case. And this idea is just based on the randomness and the equal sizes. And it means that which state, with the statistics, which states, no matter which projection we pick, it will still be fair, no matter how you distribute everything. And yes, this is a very common approach in production systems when you just want to calibrated. If we convert our Bootstrap into histogram that we wanted to show with the coin flips, we have some statements, of course. So more data points you have, the better they expect to follow the normal distribution. So this is exactly what we want to see out of Bootstraps. In this case, you at least see 80 points, and we finally can remove 2 of them on each side. And the more tests, the more A tests out of Bootstrap out of this large A experiment you extract, the better calibrated your confidence interval will be. And you can generate almost unlimited number of subsets out of this technique. So this is the end for today. Yeah, thank you for watching. This is a couple of helpful links. It is still pretty easy, very easy to Google. Just a sample size calculator and this score table, which I'm using personally when doing such type of computations. And as I promised, here's my mail. Please message me if you have more questions, and I'm happy to answer them. Recording will be available in several days. Please welcome, rewatch, and yeah, watch my first session as well. Thanks, everyone.